All right, IBAISL2 kids. We made it through semester 1. We're kicking off semester 2 with probability. So today we're going to talk about the basics of probability, which you guys probably have some experience with, but we're going to approach it from a completely fresh perspective as if you've never seen it before. First up, we're going to start with an example. If a number is selected at random from this number set right here, 1, 4, 9, 16, 25, 36, 49. So we're just going to reach in and grab one of those numbers. It says none of them are more likely to get grabbed than any other one. They all have a fair chance of getting picked. What's the probability that the number drawn will be even? Well, if you look at this, we have to count up how many numbers there are total. So there's 1, 2, 3, 4, 5, 6, 7. The way I'm going to say this, let's say n u is equal to 7. And I'll explain a little bit what that notation means in a minute, but that just means that there's 7 things. Now, of the 7 things, we're trying to see which the probability of pulling an even number. So even numbers, there's 1, 2, 3 out of the 7 that are even, because 1, 9, 25, and 49 are odd. So the probability that we're going to get an even, well, there's 3 ways that we can draw an even out of the 7. So this will be the probability. This is the probability. So the probability of getting an even number is 3 out of 7. This number on top is like the all possible outcomes. There's 7 ways that it could go down, but only 3 of them are the even. So I guess we'll say outcome you're looking for. So 3 sevens. Here's that same principle, but we're putting it into proper notation. First of all, from here on out, I'm just going to put a capital P when we're talking about probability. So the probability of A, capital P parentheses A, means the probability of event A happening. Now, the probability of event A happening is N parentheses A divided by N parentheses U. I guess, yeah, I don't have to put that. It says it right here. This top part right here, N-A, is the N stands for number of. So that's the number of ways that A can happen, or the number of outcomes that include A, however you want to say that. And then N-U, capital U, is the number of outcomes in the sample space. So the sample space is everything that can happen in the problem. Anytime you're finding a probability, it's always between 0 and 1. It's usually either reported as a fraction or a decimal. I guess we're going to kind of go back and forth between those two. But it's never like a negative number, and you'd never say, well, it has a probability of 2.5. That doesn't make sense. It has to be between 0 and 1 every single time. And the reason for that is, if you think about the fraction, the number of ways that A can happen should always be smaller or equal to N parentheses U, which is all the ways that, all the outcomes in the problem. Like, it'd be impossible for A to happen more ways than all the ways it can go in the problem. So yeah, it's always, a number divided by a bigger number, which means you're putting it between 0 and 1. So this next part, we're going to find the probability of a bunch of dice rolling situations with different sided dice. And then we're going to find the probability of each event and then decide which event is the least likely. So the least likely is going to be the lowest number probability, however you want to say that. And it looks like they're going decimals on these. So for the first one, T is rolling a factor of 24 on a 4-sided die. Well, first, the 4-sided die, I guess we'll say like this, that The probability of n of t that all the different ways things can happen in this problem with a four-sided die is you can get 1, 2, 3, or 4. I'm assuming the four-sided die has numbers 1 through 4 on it. So there's 4 ways that this problem can go. That's the sample space. Now, rolling a factor of 24, 1, 2, 3, and 4 are all factors of 24. They all divide 24. So in this case, we get that the probability of t is going to be 1. That's because every single one of those is a factor of 24. They all divide 24. So no matter what, it's going to happen. We're going to get a factor of 24. Now, on the probability of O, the number of ways O can happen on an 8-sided die. Once again, we're assuming this is like 1, 2, 3, 4, 5, 6, 7, 8 on the sides. The number of ways that O can happen, O is 2, 3, 5, and 7. Those are the prime numbers in between 1 and 8. Also, 1 is not a prime number. I feel like some people forget that 2 is the first prime number. 1 is not prime. So, the sample space here, the number of ways that anything can happen in the problem is 8. And we have 1, 2, 3, 4 ways that can go. So the probability, the probability of O is equal to 4 over 8, which is 1/2, which we will report out as 0.5. So far, the first one had a probability of 1, the second one had a probability of 0.5. Probability of D, rolling at least 11 on a 12-sided die. Well, a 12-sided die has numbers 1 through 12 on it, so the number of ways that D can happen is you could roll an 11 or you could roll a 12. Those are the only things that satisfy the conditions. So there's 2 ways that can happen. And then the number of ways that a 12-sided die can go is 12 total. So the probability of D is going to be equal to 2 over 12, which is 1/6, which is about 0.16. So far, D is the least likely event. But let's check out part C. You roll or throw at most 3 on a 6-sided die. So at most 3 means you could get 1, 2, or 3. So the number of ways that C can happen is 1, 2, 3, which is 3 different ways. And then the number of ways that the universal set or the sample space is that there's 6 different ways the die can go. So the probability of C is 3 over 6, which is 1/2, which is another 0.5. Last one, rolling a multiple of 5 on a 20-sided die. Well, a 20-sided die, let's think of all the ways that you can get a multiple of 5. So 1 is not a multiple of 5, but 5 is a multiple of 5. God, that bracket needs some work. 5, 10, 15, and 20 would be on the 20-sided die. So that's 4 different ways you can get that. And all the different ways you can roll a 20-sided die is 20 different ways. So the probability of I is equal to 4 out of 20, which is 0.25. So out of all of these, T, O, D, C, I, the lowest one is right here. It's D. So this is the least likely. This is the most likely. Couple more examples for you guys. A fair coin is flipped 14 times. So a fair coin has a heads and a tails side, and it's a a 50% chance you get one of those, or it's a 0.5 probability that you get a heads, or a 0.5 probability that you get a tails. So if we're going 14 times, predict the number of heads you would expect. This would be just taking 14 and multiplying it by a half. So this is the probability of getting heads. So, if it's a fair coin and you flip 14 times, that means we would expect that you get about 7 heads. Similar problem. The probability that a student will be absent is 0.05. That's like 5% chance. If there are 531 students in a school, how many students would you expect to be absent on any given day? This is pretty simple, that you just take the number of students and you multiply it by 0.05. When you do that, you get 26.55. So we would expect 26 or 27 students to be absent on any given day. Last one. A coastal town carries out a survey of tourists in July 2018. The accommodation type chosen and the age of the tourist are recorded. The information is in the table below. So just to break this down, like in the 18 to 30 age range, like 67 people were in a hotel, 81 were in a camper van, it's very European, and 125 in a tent, 32 in apartments. So they give us the age breakdown and what kind of accommodations they were staying in. So if we're going to select a person at random here, which age group are they most likely to fall into? Well, we need totals for all this stuff to be able to talk about any of the math. So if you add up all these numbers right here, I believe you get 305. So I'm going to add totals onto this. If you add up the next row, I believe this is 529. Then this one is 286, and then 210, giving us a grand total of 1,330 people that were in the survey. So, of those 1,330 people, the largest group that I see is the 31 to 50 range. There's 529 of them. So, if somebody selected at random, it's the biggest probability that, because that's the most people in that age range. So 31 to 50 years old would be the most likely group that is selected. What is the probability of someone belonging to this age group in Part A? Well, there's 529 of them out of a total of 1,330. So 529 divided by 1,330 is about 0.398. So it's like a 40% chance that somebody is selected from that group. The last part, 16,000 tourists are coming to town. Hotels only have capacity for 5,000. Will they have enough rooms? So we're going to base this off of this data, but now we actually need totals for the hotel. I guess we could do totals for all of them. So if you add up all of the hotel numbers, you should get 370. So I'm doing totals. And then total for camper vans are 419. Totals for tents are 247. Total for apartments are 294. And all those should add up to 1,330. People that are staying in hotels are 370 out of 1,330. So probability of a hotel person is 370 out of 1,330. That number, I guess we don't even really need that number, but that number is going to get multiplied because that's the probability that somebody will stay in a hotel, we're going to multiply that by 16,000 people to see about how many of the 16,000 would stay in the hotels. This is assuming that people kind of stay in the same ratio as the data up here with the 16,000. When you do that, you get about 4,451. So people in hotels, which means they are just barely under the 5,000 limit. So yes, they will have enough capacity. All right, you guys, good luck with your homework. Please ask me questions in class.